Our sun is a mid-sized star surrounded by other stars spread out in space. That's what you're looking at in the nighttime sky. But what you see looks more like this: points of light on a celestial sphere all moving together, rising in the east and setting in the west, circling the North Star. So how do we go from this sphere, which we see, to the ocean of stars described by the textbook? Here's a concrete example from the winter sky. These two stars, as you can see, are about the same brightness, but your textbook says that they are not the same. This one is closer and smaller. That one is much bigger and much, much farther away. Well, says who? How do we know the distance to the stars? It's a big question. Humanity's place in the cosmos. Finding the answer is an ongoing group project, and we'll take it in 3 steps. Number 1, it all starts with parallax. Number 2, brightness versus wattage. And number 3, the HR diagram. If it starts with parallax, we should know that that is the change in observation based on viewing position. Parallax is how we found the size of the Earth, the distance to the moon, the size of the solar system, and, after a long wait, the distance to the closest stars. It all starts with parallax. But what is parallax? It's the reason the world looks a little bit different from your left eye than from your right, the reason you have depth perception. Or consider this brave explorer. He has just landed on planet Table. He looks up and sees 2 towers, one red, one green. They look about the same, but that doesn't mean much. After all, those 2 stars look the same too. Let's find out if one is closer to the other, not by walking towards them, but by moving like this. I hope you agree that the green tower is closer, but how can I put that into words? It moved against the background less, or something? Well, yes, the green tower is closer. They only look the same because the red tower was bigger and farther away. Let's be clear about angle, physical height, and distance. Viewed from the same distance, red is obviously taller and covers a bigger angle. Here they cover the same angle because red is farther away. Great. But exactly how far away is it? To find out, let's make some observations. Draw a line here, observe it there, walk over this way. Measure, observe again, measure angles, and call on help from geometry. Side angle side theorem, anybody? I hope you agree, though, that there is enough information here to find the unknown distance to the red tower or to a star. The Earth swings 93 million miles to one side of the sun and then 93 million miles the other way. That's a huge baseline. We must be able to measure parallax to the star. Right? Wrong. Pretend that's the North Star. People, including Aristotle, looked and looked for measurable parallax to this or any other star and never found any. And by never, I mean not until the 1800s. Before that, it really did look, even with the best telescopes, it looked like we lived in a celestial sphere. It all started with parallax. Today, the hunt goes on. Well, technically, this mission ended in the 1990s, but this mission was active in the 2020s. I did want to mention Hipparcos, though, because that mission did what Aristotle couldn't. It found parallax to Polaris. That allowed them to calculate the distance to the North Star, and feel free to stop here if you want. How do you know the distance to the star's parallax? Brute force. But there's something funny that they did when they got that value. The first thing they did is they compared it with other calculated values, or other guesses, other values that had come before. So where did those values come from? It all starts with parallax, but it does not end there. Brightness isn't wattage. Remember all that fun we had with angle and height? This is basically the same thing, only this time we're thinking about the total energy released versus what part of that energy we receive. These 2 lights are the same distance away. The higher wattage bulb is brighter, obviously, but if we put them at different distances, that would no longer be the case. Here they have the same distance, here they have the same brightness. And, just like with height and angle, it's all connected by distance. The math is not exactly the same, but the point is, if you know 2 of these values, math can tell us the third. And that's good news for our explorer. He climbs off the table and onto the roof at night, and then he calls his partner. So this is a phone conversation here. Hello, let's start mapping out the planet. You've made it to the building, right? Great. Now flash your lights on and off so I can find you. Okay, I found you. Now, leave the light on so I can measure its brightness. Got it. One more thing. Now I need you to tell me the wattage of the light. Look at the package. There. That's it. What? Okay, yeah, I know we're talking about lumens technically and not watts, and technically I want to know the luminous flux, the energy released specifically as light, not the wattage. That's the total energy used. All right, listen, I gotta go now, all right? Bye. But with a measured value for brightness and a known wattage, okay, fine, a known luminous flux, we can find distance. But how do you do that with stars? How can we find the luminous flux, or call it luminosity, or just stick with wattage? How do you find that to a star? Again, it all starts with parallax. Brightness versus wattage, they are not the same. And number 3, the Hertzsprung-Russell diagram, which is weird. The axes are weird. The x-axis, spectral class OBAFGKM, is weird, and that's related to temperature, hotter to the left, and to color. It's related by this thing called black body radiation, which I don't want to get into. We'll leave that to physics. I want to do something else. I want to measure it. Consider this, the spectrum of an O-class blue star. And these are the spectral lines, the color fingerprint, the color barcode. Here's a more detailed picture of that spectrum. Good thing we're friends with the physics and the chemistry, because we're going to need their help on this stuff. Like I said, it's a group project. O, B, A, F, G, K, M. Spectral class. So pick a star, analyze its spectrum, and then name it. F5, that means halfway between F and G. Now let's do it again. B8 and F5, so now what? Now the watts. Get it? Wattage, the y-axis. This one's weird too. Just whatever you call it though, don't call it brightness. These numbers refer to absolute magnitude, a strange inverse logarithmic scale which tells you the luminosity, higher wattage on top. And look, with this diagram, there's room for stars with a luminosity of 10,000 suns, which is crazy. But none of them, of course, are as bright as the sun, which is so close. Nice diagram, but it's empty. Time to fill it in. But how? It all starts, say it with me, with parallax. That tells us distance. Next, measure brightness. That way we can find wattage or luminosity or absolute magnitude or whatever you want to call it. Good. These are the closest stars, all within 20 light years of Earth. And this one we've seen before. By the way, these parallax angles, and you have to take them 6 months apart, they are between 0.8 and 0.1 arc seconds. An arc second is small. Don't try to measure it with a protractor. It's the angle covered by a dime held 2.5 meters away. Well, did I say meters? I meant 2.5 miles away. That is an impressive measurement, but this is a super boring graph. It's somewhat linear, not that that means too much. Our axes are so weird. It's boring because physics already told us that hotter objects put out more energy than cooler ones. But then again, maybe this line is all we need. We found the spectral class of that other star, remember? We couldn't find its distance with parallax. This is way before the Hipparchus mission. But if we could use this line to find out the wattage, then we could calculate distance. But I don't love this solution because it assumes all stars are pretty much the same, and our textbook says that they are very different. What will we do? We'll improve our telescopes, improve our measurements, find more parallaxes. These stars are all within 100 light years of Earth, and this is exciting. The first person to publish this HR diagram was Hertzsprung himself in 1873, but in the very first sentence of his paper, he credits two others, Antonia Mauret and Annie Jump Cannon, awesome name, Annie Jump Cannon, who were both working at Harvard with finding these exciting new stars first. What are they? Well, they're stars with the same spectral class and the same spectral lines and the same red color as other stars that are closer, but these stars have much, much higher wattages. How is that possible? They must be gigantic. And I said that these stars had the same spectral lines, but not exactly the same spectra. These new giant stars have narrower lines, so they look different. You can tell the difference, and the physics people say that this makes sense too. And now comes the really fun part. You can see by the picture here that the HR diagram has room to grow with binary stars like Algol. Now technically it's a 3-star system, but we'll add 2 new stars onto the diagram at B8 and A7. And also Algol is technically within our self-imposed 100 light-year limit, but here's the fun part. It doesn't need to be. That's because the spectrum of our A7 star is so similar to a known star that we know its luminosity. That means we know its distance. That means we know the distance to the blue star also. That means we can find its luminosity. And that means we can plot the B8 star without parallax. We'll go through that again. Binary stars. One of them's known. Since we know its wattage, we can find distance. The other star was unknown, but now we know distance and brightness. We can find wattage. We can put it on our HR diagram without parallax. 2 more really quick examples. Antares, a double star system, B2.5 and M1.5. But how is that possible? How can the redder star be so much brighter? Only if it is a supergiant. Same thing for our friend Rigel. Remember him? It's another multi-star system. Graph 2 similar spectra, B8 and B9. They're the same distance away, but how can that B8 star be so much brighter? Only if it's a supergiant. And no wonder Aristotle could not find parallax to Polaris. It's a far-off supergiant too. It's also a variable star. I don't want to talk about that. And there we are. And here's some more. Noticing patterns. Limiting ourselves to 3 different kinds of star. And now let's try it out. On this guy. Mu Geminorum. Not one of the brightest stars in the nighttime sky, but we can measure its brightness. This value is in something called the apparent magnitude scale. It's another inverse logarithmic scale, so bigger numbers mean dimmer stars. Next, let's find its spectrum. And there it is. We can notice that is a M3 spectrum. Now observe the width of those spectral lines. This is a giant. This is us graphing an M3 giant on the Hertzsprung-Russell diagram. That is its absolute magnitude, its wattage, you could say. I'd say maybe a value of -1 estimating there. And with wattage and brightness, we can find the distance. And if you're looking for some mathematical details, here they are. Apparent magnitude is what we observed. You had to take my word for that. Absolute magnitude, I estimated that using our HR diagram, and we can divide by 5, and then we can do that and find a distance of 59.2 parsecs, and there happens to be 3.26 light years per parsec, so our value is 193 light years. Look it up on Wikipedia. Their value is 230 light years. They were using a more precise absolute magnitude of -1.4. And of course, their value is better than mine because they're relying on those space programs that measure the parallax directly. But I'm trying to do something a little bit different. I'm trying to show you how over centuries, mathematics and physics and chemistry and more observations than you could possibly imagine can all come together in a group project that finds humanity's place in the cosmos by measuring the distance to the stars.